Welcome back, guys. Now in the last class we saw that in n-type semiconductors the majority carriers are electrons and the minority carriers are holes, and in p-type the majority carriers are holes, the minority carriers are electrons. But such a piece of extrinsic semiconductor is not of much use to us because they are electrically neutral. So by a special manufacturing process, a pure piece of intrinsic semiconductor can be so doped that one half of it is p-type and the other half is n-type, and a p-n crystal like this is called a diode, and the border between p-type and n-type is called p-n junction, and it is this p-n junction which has a very remarkable property that paved the way for the inventions of all the electronic gadgets that we use today, as a p-n junction is the basic building block of many semiconductor devices like diodes, transistors, op-amps. Therefore, it is very important to have a very clear understanding of the junction behavior in order to analyze the working of other semiconductor devices. Now, let us have a look at the formation of a p-n junction. Now, consider a silicon semiconductor wafer doped with trivalent and pentavalent impurities. Suppose this is p side and this is n side. Now, two important processes occur during the formation of a p-n junction: diffusion and drift. We know that in an n-type semiconductor, the concentration of electrons is greater than the concentration of holes. Similarly, in a p-type semiconductor, the concentration of holes is greater than the concentration of electrons. And during the formation of p-n junction, due to concentration gradient. So what's gradient? Gradient is basically difference. Due to pressure gradient, air flows from high pressure to low pressure. Due to potential gradient, current flows from higher potential to lower potential. And similarly, due to concentration gradient across p and n sides, holes diffuse from p side to n side and electrons diffuse from n side to p side. And this motion of charge carriers give rise to diffusion current across the junction. Now, when an electron diffuses from n side to p side, it leaves behind an ionized donor on n side. Now, this ionized donor, which is positive in nature, is immobile as it is bonded to the surrounding atoms. And similarly, when a hole diffuses from p side to n side, due to concentration gradient, it leaves behind an ionized acceptor which is negative in nature. And as the electrons and holes continue to diffuse, a layer of positive charge on n side of the junction and a layer of negative charge on the p side of the junction is developed. And this space charge region which I am drawing now so this space charge region on either side of the junction together is known as depletion region. This region is known as depletion region. And because of the immobile ions piling up on either side of the junction, a potential difference develops across the junction. And an internal electric field EI directed from positive n side to the negative p side. So EI directed from positive n side to negative p side is developed, and this electric field opposes the diffusion of electrons and ultimately it stops further diffusion of free electrons across the junction. And the width of this depletion layer is of the order of 10 to the power minus 6 meter. The potential difference developed across the depletion layer is called potential barrier, denoted by V0. And at 25 degrees Celsius, for silicon diodes, the potential barrier is approximately equals to 0.7 volt, and for germanium it's approximately equals to 0.3 volts. And this internal electric field enables the minority carriers, that is electrons in p region and holes in the n region, to flow across the junction. And the motion of charge carriers due to this electric field is called drift. Thus, a drift current, which is opposite to the direction of diffusion current, starts. And this drift current is also known as reverse current, and its value is obviously very small. And ultimately, an equilibrium condition is reached when the small reverse current exactly cancels the diffusion current, and the net current across the junction is therefore zero. The barrier potential depends on the junction temperature. An increase in junction temperature creates more free electrons and holes in the doped regions. As these charges diffuse into the depletion layer, it becomes narrower and narrower. Now this means that there is less barrier potential at high junction temperatures. Now I guess it's not required for you in 12th standard, but we can state a rule for estimating the change in barrier potential. And the barrier potential of a silicon diode decreases by 2 millivolt for each degree Celsius rise in temperature. Mathematically, it can be written as delta V by delta T is equals to 2 millivolt per degree Celsius, or delta V is equals to minus 2 millivolt per degree Celsius into delta T. Fine. So what's the difference between PN junction and a PN junction diode? A PN junction diode or semiconductor diode is basically a PN junction with metallic contacts provided at the ends for the application of an external voltage, and it is represented by the symbol given on the screen. Okay, so this side is P side, which is positive, and this side is N side, which is negative in nature. In reality, this is how a diode looks like. This one is IN4007 diode. As you can see here, the silver stripe is the N side and the other side is the P side. I'm just showing you so that if you encounter it in future, you can identify the P side and N side. So that's it for today, guys. See you in the next lecture.